Hello, everyone. Thank you for having me here. I'm Prasun Mahanti. I'm from Arizona State University. I'm the deputy PI for ShadowCam instrument on the KPLO mission. So this talk is about something really specific. It is extremely strongly related with pyroclastic, but I'm not going to go into pyroclastics. This is more of a show and tell that what we can see now, which we could not have seen like 14 years back when the LRO mission started. So I'll take an opportunity here because we've been talking about PSRs here and there. So I just wanted to have a very brief overview of the PSR itself. Uh, so the moon's axis has a very small tilt, and then the sunlight reaches at grazing angles. Uh, because of that, the topographic lows are going to have less of the direct illumination, some direct sunlight, and the no direct sunlight on the base. And then on the sunlight, you have like a crescent of the direct illumination, and the inner lower walls and the floor, you have the permanent shadow. Now, PSRs can be very cold because there is no direct illumination. The emphasis here is on the word can be, and I'll get to that later in the talk. So here's a question. Which one of these is a PSR? Like, it's an elevation profile, right? So here's the thing. All three of them are actually PSRs. And this is taken from the Schrödinger basin. Now, out of those, as you can see here, probably it's not visible in here, might be visible there. There are about 50 small PSRs inside the Schrödinger basin. And these are 50 regions that never get direct sunlight. Out of these three, two are craters. The other one is a volcanic vent. So PSRs are not stuck with craters. They are stuck with topographic depressions. Why can we see inside PSRs if there is no direct light? That's because the illumination there is scattered. And here's one small simulation slash modeling, which actually kind of gets you quickly through the whole thing. So from the sunlight, you have the direct illumination. And from the direct illumination, you actually have rays coming from the scattered from the directly illuminated zones to a point at the PSR. Now, if you do that thing all over from every point that the light is coming through, what you ultimately get is actually the secondary illumination, which actually lights up the PSR. And that's the reason why we can take images inside PSRs. Now, if you integrate it over the diurnal component over the entire time, then you get this whole thing happening, which is right now active at all these PSRs, right? And depending on the location in latitude, depending on how much sun actually getting through, that controls their temperature, that controls the possibilities of having something which is not sublimed as long as now. So I'm not going to get into the illumination part of it, but we have quite a few papers. The first one here is the algorithmic development and implementation. Next two are basically based on ShadowCam images and what we have seen so far. So we do have inside these shadows, we actually have light. This image here is a little bit old, actually. So in 2009, this was the situation for the South Pole mosaic. And you can see here inside Shoemaker, this happened about like 4 years from then. This is the long exposure NAX. And this is right now with respect to ShadowCam in 2023. So you can now see clearly inside the Thule crater inside Shoemaker. So the boundary there in that white thing that you can see, that's the nominal mission for ShadowCam. That's like the 80-degree mark. Now, what happens is, because it's a polar orbiter, we actually keep on taking images outside that thing. And here is where the topic of this talk is where you have the Schrödinger basin, right? As chance would have it, we actually have a ShadowCam image going through the exact vent that I'm going to talk about, right? Or the other way around, right? So what we managed to do is that we managed to get a stereo image at that point. And here's this other thing that I wanted to talk about. So PSRs are not always cold. Just because there is no light doesn't mean that it is going to become so cold that you can trap volatiles. So here's something actually I spoke in the last ELS. There are two PSRs which are kind of the same size, but they have a 40 Kelvin temperature difference. So it all depends where that PSR is there and how the topography is working. Okay, so this is one of the outputs from this particular presentation. So the temperatures in the PSR within the vent is observed to vary between 60 kelvins to 160 kelvins. What does that mean? Well, it means that the temperatures within this PSR is much higher than the usual volatile retentions. So contrary to some of the earlier thoughts, we do not think that there is a scope of actually finding volatiles inside this particular PSR. Okay, so now let's look inside the PSR. What does the vent actually look like? That's what we have not seen ever since the NAC images came out of this thing, right? That's what it looks like. As you can see, it's a typical volcanic formation. The inside is smooth. You don't see any long fissure. You don't see any true circular vent. We don't see any kind of caldera kind of formation like a slumping. They appear recent, but you need to take into account. So why do I say they appear recent? Is because you see this sparingness of craters, right? But you need to take into account two things. Number one, it's a pyroclastic target. Number two, the slopes there are quite steep, which means there is a lot of surface process which is active. And I'll show you some indications of that. So the sunlit and the shadowed part of the vent. So this is the part which is coming from the LRO NAC. And in the sunlit part of the vent, there is an evidence that you can see there is a stratigraphic interface, like where you can see this outcrops. And there's a linear bench on both sides of this. So when this thing came out, usually you would expect something to be on this southern part of also, but that part was hidden in the permanent shadow, right? Now we can see that, and we actually see the same kind of outcrop in the southern part inside the PSR. So now if you take into account the contour at which these things happen, what you see is that the shadow cam images show similar exposures at pretty much the same elevation contour at about minus 4,800 meters. And you can see two outcrops. One is just outside the PSR outline there. The two outcrops are separated by about 400 meters, but they all appear more or less at the same height. What does that tell us? Is that you have a stratigraphic interface there, kind of a bench formation there, over which the pyroclastic thing really happened. So, we're looking at these legs of this bench, and, 3 legs are better than 2. And from the cytochrome stereo, we can now have an added confidence of the elevation level of the pre-existing surface for this pyroclastic activity. And what does that blend into? It blends in as to how much was the maximum thickness of the pyroclastic thing that is out there, and overall it changes the volume calculation. And it's not part of this presentation, but we are working on that. The maximum deposit thickness of the pyroclastic layer is approximately 500 meters. This is similar to the previous estimates, but the maximum vent depth is a little bit larger than what was expected from earlier. Okay, so the other thing that we could do from our stereos from ShadowCam is that we can now actually try, and from the level of topography, we can actually now look at slope processes. And here is a tool that actually I'm using for, we have recently used it for another work in the Shackleton PSR. So we are using something called as the horizontal curvature. You can see that this is part of most remote sensing analytical packages. So what it does, it actually shows you how the flow of different, flow of regolith and flow of rocks, how does that happen? If it affects the topography. And because ShadowCam stereos are resolvable down to 6 meters, at least, you can actually see these things happening. So this is one example of the slope process inferred outside the vent. So this is from the LROC NAC. So you can see this is the edge, the same as that edge there. And then you can see these things happening. And this is coming from topography. So this is not image. So there is substantial depth to these things so that as to make an impact on the topography. And this one, again, is within the vent. So again, you can see similar formations inside. So the vent inner walls show shine, so mass wasting, flow of dry regolith, loose rocks towards the lowest point. Near the lowest point, you can see loose rocks. They seem to form really good-looking patterns. And some of these mass wasting signatures, they appear to be landslides, probably caused by impact events. If you look on the outer rim of this vent, you can actually see quite a few impact craters. And our current belief is that those craters caused this mass wasting thing to start in the first place. Most of them, not all of them. The horizontal curvature features are similar. Now, this we actually have a quantitative evidence of this thing. not presented here, but what this show that they are similar on the illuminated as well as the not illuminated parts, suggesting similarity in the properties of the loose pyroclastic regolith layer. And in the shadow cam images, the surface nearly lacks all craters, which suggests continuous resurfacing from mass wasting, as well as due to the target property of the pyroclastics. So closing remarks, shadow cam is acquiring images inside PSRs. We are filling the gaps and the gores and closing the knowledge gap. We have acquired images and stereo at the permanently shadowed Schrödinger G pyroclastic vent. Our initial analysis reveals it's filled up vent about 700 to 800 meters deep. It confirms stratigraphic boundary at about 500 meters. It has very few craters because of the pyroclastic target and the active surface processes. And the temperatures within the PSR are much higher than usual limits for volatile retention. And more details, and hopefully a paper would come soon. So keep in touch and look at our data sets. And if you have any questions regarding the ShadowCam data, please don't bother to, please don't feel restricted to ask me. Thank you.
Hi, Prasun. Josh Cahill, APL. So I know of at least one prism suite that proposed to go by rover down into the vent. Can you say anything in terms of what you're seeing in terms of hazards? Would it be safe for them to go?
Okay, so from whatever we have seen so far, I think it's pretty steep. We are trying to get some idea about the geokinetics from some of these things that I showed. So right now, I cannot comment more than that, but yeah.
Hi, Carl Hibbs, APL. Nice talk, really nice images. The question is on the rate of mass wasting, because they point out some of the temperatures are pretty warm for where water ice to be stable, but everything's very time dependent. So if mass wasting occurs relatively quickly, water ice could remain stable long enough to be buried. Do you have any insights into the rate of mass wasting into the pyroclastic event?
Not at this point. Not at this point. No.
Okay, thank you.
Hi, Gareth Morgan, PSI. Yeah, great talk. What do you think the nature of the stratigraphic boundary is?
The height? Or?
Oh, the nature of it. What's it separating? Is it two different units or?
We think that it could be, it's not like the usual basalt kind of, but we think there is some plagioclase. That's what we are checking right now.
Thanks.
I have one question. Hello, my name is Monica Borwa, and I am a first-year PhD student at Open University, and my work basically is associated with measuring water content in lunar interior. And something that I have come across in literature is that when we talk about pyroclastic deposit, we think about orange glass, where back then researchers has measured the indigenous hydrogen content of about 5 to 30 ppm. So in a PSR, if you have a pyroclastic deposit, can you think, is there a possibility of something finding that we found in Apollo 17 and that could make the inventory of the PSR much more resourceful?
Okay, so if you're asking if the PSR makes it more useful?
Presence of pyroclastic deposit in the PSR, does it quantifies the its potential resource for ISRU?
Well, from a very cursory point, I do not think that being a PSR really helps in the ISRU, apart from the fact that it's going to be difficult to row. But most of these cases where you have PSRs, especially for this one, the slopes are so high that the difficulty in actually getting to this thing is far dominates the effect of ultimately getting to, like, if you're thinking about like water or titanium or things like that.